Okay.
Hi, hello everyone. Good morning, good afternoon, good evening, wherever you are. Thank you for joining the Geoscience and GeoEnergy webinar of today, 12th of November 2020. Sebastian and I are grateful to our keynote speakers and you all for supporting this initiative and to combat work from home isolation. Please do subscribe to our channel and access the past talks in the case you have missed any of them. There is also a Tea Time Talk series run by mostly junior researchers for junior researchers and others as well. Please, PhD postdocs, do attend, volunteer to give a talk and participate and build up your network. Sebastian and I also are actively thinking and designing the end of the year and Christmas program to feature all of you in the channel. News and details about this would come out soon in due time through our channels in Twitter, LinkedIn, and other ways as well. Now, without any further ado, let me introduce the speaker and the topic of this week. It's our great pleasure and honor to introduce our dear colleague and good friend, Maren Brehme is our keynote speaker of this week. Maren is assistant professor of geofluids and geothermal engineering at TU Delft in the Netherlands. Actually, she's my very direct colleague. We are in the same group as well. She holds this position since 2019, last year. Before joining TU Delft, she had worked with a German Research Center for Geosciences in Potsdam, Germany, for almost 10 years. She is an active researcher and scientist in geothermal engineering field, going to the field, collecting data, coming back to the lab, look at the fluids and other things with all the fancy stuff she does, and I try to catch up with her what she actually does with those collected data samples, coming to the lab, sitting behind the computer, analyzing them and studying them. And all in all, to understand how the geofluids behave and what properties they have, how geothermal systems work, and how can they be utilized more sustainably and efficiently to provide low carbon, affordable energy to the society. Recently, she has been also awarded as a lead PI a prestigious grant, ITN, International Training Network, called EasyGo. And I'm sure that the subject is not as easy as the title says, but the title is EasyGo. And under the EU Marie Curie action related to geothermal operation with 3.5 million euros and having 14 partners. And currently with her colleagues, she's appointing 13 PhDs at 4 different universities. And I was chatting with her the other day. They have received plenty of applications, about between 50 to 100 per open position. So about 1,500 applications they should go through. So that's quite, I guess, a challenging task now for them, for all the colleagues who got this. Congratulations to them. But we wish that you end up with having the right people in the team as well. Please visit her Google Scholar page and get in touch with this young, passionate, and cool scientist. I can endorse all of them. I work with her quite closely, and it's a pleasure and honor for me to be a friend and colleague. And get in touch about all the geosciences, especially also in particular geothermal field as well. It's a pleasure and honor to host you, Maren. Both Sebastian and I are really pleased that you accepted our invitation. To the audience, please note Maren's lecture will last for about 30 minutes, followed by questions and discussions. Like always, I open this and Sebastian will chair the discussion session. Please type in your questions in the chat room, and after the talk, Sebastian will go through them. Do not wait until the end of the talk. Whenever you think it's appropriate time, just text your question. It may also trigger other questions also. Maren, thank you very much once more. Please start your presentation.
Thank you, Hadi, and thank you, Sebastian, for the invitation. Of course, I'm very happy to present here, and thanks for the nice introduction. Thanks for your effort also to keep this series of webinar up since even March. I know, because I sat on the other side already, what that means. A lot of work, a lot of effort, so thanks for that, for keeping us in touch. So let's start with the topic of today, how to sustainably develop and operate geothermal systems. Let's directly jump to a basic problem or challenge we have during developing and exploring new geothermal fields. Here you see a statistic of the worldwide drilled wells for geothermal energy, and on the x-axis you see the well capacity, and on the y-axis you see the number of wells drilled. And what is really important here is that most of the wells you see here, for example, are producing 3 megawatt electricity. And only a few wells drilled worldwide are producing about 15 to 20 megawatt electricity. But you know, of course, the drilling costs are very high. It's about €1 million per kilometer. So rather, it would be nice if we could shift these statistics a bit to the right. So if we would rather drill most of the wells in the range of 15 to 20 megawatt electricity, but not in the lower range of 3 to 5. So that brings us already to a major challenge, and this is the worldwide statistics, and I studied a lot of fields. For example, here the Indonesian field Lahendong, they drilled a lot of wells which have been non-productive even, and only a few wells which produce now 20 megawatt electricity. Another example from Theisterek here in Iceland also shows the same statistics. Only a few wells produce a high amount of electricity, and a lot of wells range in a megawatt electricity between 6 and 7. And I even found a statistic for drinking water wells. So this is not only about geothermal, it's about subsurface reservoirs. And these statistics from 1982 shows that a lot of drinking water wells at that time were drilled with a low production, and only a few wells with a high productivity. So that is one of my focus in my research, and I found this study from Peter Leary. I really can recommend to read. He wrote down nicely this behavior of wells in a physical mathematical way, which connect the porosity, permeability, and the fluid flow in the wells. And he observed this in well capacities, but also well logs, and observed that there's a logarithmic change between in permeability, which is controlled by a factor called alpha, which is actually constant, and he found that it's 30 to 45, with a porosity between 10 to 30%. So if you want to go more into the theoretical background, I recommend to read this paper. But let's see let's dig a bit deeper into these high productive wells. So what is going on in these wells? If you check, for example, this field again in Lahendong, what does it mean to make it a bit more clear, a bit more visible? This is the drilling history, basically. So you have the well capacity on the left now, and you see that the 2 green wells here drilled at the very end. So they first drilled about 25 wells before they found these high productive wells. And they produce with a temperature above 280 degrees and about 650 tons per hour. But it would have been nice if they would have drilled these wells first. So first find these high productive zones in the geothermal systems before they start drilling. So that brings us to the question, how can we improve the exploration techniques? And if we now look into these 2 wells, for example, we come to another physical mathematical description of this permeability distribution in the underground, and it looks a bit different than people sometimes think. So there's no spatially uncorrelated field of permeability. There's no like random distribution of the permeability in the underground, but there's a clear spatial correlation between these permeable zones, and you can calculate that. It comes down to a factor of the scaling exponent between 0 and 2, and you will see if you put your own well logs, and I invite you to read the paper and do that with your own code, you end up normally with an n about 1. And I put some examples here, and that means the permeability is especially correlated, and that if you then go into practice, on the left lower picture, you see, for example, deviated wells, drilled horizontal wells, which target some permeable zones, and you see like kind of clouds, light green clouds, which demonstrate the permeability fields. So we cannot expect our wells to tap all these permeable zones, but first we should explore them and find them. And therefore, like Hadi mentioned in the beginning, I go to sample on sure what is telling us. So our first step normally done by exploration geologists is a structural geological map. And of course, we on that a field structure. You see setting, they are either thrust faults or normal faults. You also see two types of faulting. There's a black one, which is an older faulting system, and then this one is overprinted by the green faults, which are north-south or east-west oriented. They are normal faults. How can we understand which is the older or younger system is sometimes a question. So I put this picture in the right bottom. You see that two faults here are cross-cutting each other, and therefore we understand that the cutted fault is the older one, overprinted by a younger one. And that is something very nice you can do in the field. Then what we have done also is discharge measurements in rivers, but let me first explain why we did this. So we have this nice structural geological map which tells you about cracks, fractures, and probably pathways for fluids in the underground. But you never know. Faults can also be barriers for fluid flow. So to find these permeable zones in the underground, we also we target for faults, of course, especially in these tectonic active areas. But we have to take care if there are fluid conductors or fluid barriers. So here we used a kind of old but also new technique. It's a simple tracer test. So you see in the picture, we used normal buckets with salt water, put them into the river, and observed at a lower point in the river how this salt water then is transported in the river, and how much of the salt water is coming to our next measurement points. And you see here on the map, we measured this at several points along the river. And what normally should happen is that you get a kind of peak, like you see at the right side, a tracer peak where you observe how the salt water, because you can't see it, but you can measure it with the electric conductivity over time, is flowing in the river. What normally should be is that the river downstream is growing. So a river starting in the mountains typically is a small creek, but then grows and grows, becomes a big river at the end. So we checked this for the smaller rivers, inflows and outflows of this lake. You see here in the center of the map. And let me show you the results. These are now the numbers calculated back to liters per second of flow discharge in the rivers. And you see it's 44 to 39, and then after the lake, the outflow of the lake is a bit higher. So there's also some inflow from the lake. It's accumulating. So basically it's getting more along the river. But what is interesting here is that between 44 and 39, we see a loss of water. And also between the second 2 points, 76 to 64, there's a loss of discharge in the river. And this, like explained before, shouldn't happen actually. So there should be an increase, but we see a decrease. So our interpretation is that because it just happens right next to these two faults here, bordering this extension basin around the lake, they are kind of sucking water out of the rivers, or the river water is infiltrating into this fault, which shows us there's a kind of permeability here. So we see a loss of water of 5, and then crossing the second fault, even about 12 liters per second. This is quite interesting and kind of new technique we now use to understand or get a feeling for the permeability of the faults. So we don't not only map the faults, but also try to understand about the permeability. So translated to a cross section, which is covering the two faults you see here on the right. We checked this with the well data we had. So there are also geothermal wells, which you can't see in the map, but here in the cross section, that the temperature also drops down close to this fault in the northeast. So that also confirmed our interpretation that we lose river water, which is of course colder than the reservoir water. The river water has probably about 25 to 30 degrees in a tropical environment. And in the reservoir, we have 250 to 300 degrees. And you see a clear drop close to the fault on the right side. So that confirmed our idea of cold water infiltration into the reservoir, which is, of course, also not so nice for the wells drilled close to that, which should produce hot water or steam even. Then we put that into a quite basic, simple model, and modeled the temperature and pressure distribution calibrated with the well data. And again, we see that on the top you see the lake, and then there are 2 or 3 faults, that there's a clear drop of temperature, at least on the northeastern fault. On the southwestern fault, this impact is not that clear. Also, the data points are not that good in this area, but on the northeast, there's a clear drop of temperature also in our model. So the question would be now, when you look at the map, these 2 green wells we are talking about are the 2 high productive wells I showed in the beginning. And the question would be, okay, if this is so nice to produce here, shouldn't we drill more wells in this area? Then let me introduce another problem we have with these 2 wells. This is about the geochemistry. So these 2 wells produce 20 megawatt electricity, each of them, which is very nice. But they also produce a fluid with a pH of 2, which is not very feasible for the casing, not very safe for a sustainable operation here. You see at the bottom right a corrosion test done by my colleague Amila Kisevich. She tested casing, steel material, with the brine from that wells, and also with the brine from a close-by well, which is the red dot. It's a dot because it's a vertical well. The green ones are deviated towards the lake. And you see already from the picture that there's a lot of corrosion and chemical reaction happening on these steel pads she tested here. The interesting thing is that these LHD5 and LHD23 are quite close together. So the green wells and the red well are just across the fault. And we just realized that this is the fault with a permeability here. So what is happening? Why is the chemistry so different, so close to each other? And they are only, let's say, 200 or 300 meters apart at the subsurface. So what is going on here is the question, and everything is happening on such a close location to the lake. So we applied for another project to focus a bit more on this lake. It's called Lakelina, and you see a picture here, a panorama picture. You see our measurement set up, and the team I've been working with and leading for this field campaign in 2018 and 19. And you see a simple sketch of the lake with the inflow of the river we talked before about, and the outflow, and some hot springs around. There's a geothermal power plant, and there are some wells left and right of this lake. And we expect a magmatic heat source beneath the lake, and some kind of interaction between the geothermal reservoir beneath the lake and the lake water. One interesting thing to remember here is that also the lake, not only the well fluids, but also the lake water has a pH of 3. So there's we expect kind of a connection between the acidic reservoir water and acidic lake water. So that was our motivation to do a bathymetry study of this lake. On the left side, you see a map of our measurement setup. So we rented a small raft and drove in kind of circles around this lake, first the big ones, and then entering the center and closer loops. And then you see some red dots and some smaller circles, which we investigated a bit more in detail. On the right side, you already see the result of this bathymetry study. And you see that the lake has a depth of, of course, 0 to about 10 to 12 meters on average. And there's a much shallower area in the eastern part. It's not so steep, and it's much steeper on the western part of the lake. And then you see 2 points already labeled with Geo1 and C11, which are deeper parts. So you see it's up to 30 meters deep, 20 to 30 meters. And all of these deep parts are located in the western area, steep shoreline of this lake. If we look into this a bit more in detail in 3D even, you see a really interesting structure which surprised us a lot. We never expected such deep holes in this small volcanic lake, but they are not even pockmarked. They are really steep cones, up to 30 or 35 meters deep, and they are all aligned along the western shore. And we were even able to cover them on pictures, which you see at the bottom, when we were crossing them with a small boat. And they are so impressive, and sometimes we even see bubbles coming out of them and bubbles at the surface of the lake. So there's really activity coming out of fluid flow activity coming out of these 2 holes. On the top right, you see already our interpretation, because the goal was to see also faults at the lake bottom. This is a quite nice technique, because the lake bottom normally is not that eroded. Like, for example, here we are in a tropical environment. It's hard to find outcrops. It's hard to see structures onshore, but offshore, beneath the water, it's just covered by water. And if you pass the water with the bathymetry tool, you can see faults, and they are quite nicely seen in our results here. What we also did is, on top of the bathymetry, we took geochemical profiles, and I just want to present 4 of them here as a comparison, representing an average and then representing the 2 deep holes you already saw in the bathymetry, the Geo1 and C11. We took measurements at 52 points, but these 4 are quite representative for what happens in the lake. So the E3 is kind of the average profile for the lake. You see in blue the temperature, which is of course decreasing towards the lake bottom. Then you see electrical conductivity, which is basically salinity, first a bit increasing and then also decreasing. The density is increasing. And then we took pH measurements over depth, and that is also a bit increasing. But now let's focus on the deeper holes, which are much more interesting for us, especially Geo1. So the Geo1, you see that also the temperature in blue is first decreasing, but then after about 15 to 17 meters, the temperature is increasing again. And there are a lot of bumps and peaks now in the line. It's not so smooth anymore. And then the same happens in salinity. Also, salinity is slightly increasing, even since 5 meters depth. And then if you compare the peaks you see in the lines, in the measurements, they are correlating. So salinity and temperature are increasing in smaller peaks coherently at the same depth. And that's why I put these blue arrows here, which are interpreted as water inflow from the deep hole. So you think of that the average lake bottom here is about 12 to 15 meters deep, and then this cone, this deep hole starts, and we immediately see that hot and salty water is inflowing into these holes. And this is quite exciting. We measured that with this orange tool you see on the picture. Also, it's very simple. You just drop it into the water. You have to steer your boat such as that you're on top of the hole, and then you take a measurement until 35 meters depth. You just drop it down and pull it out again, and you have these nice measurements. We did that for 52 points, 3 times per point, and the data fit quite well. What is also interesting by depth is the pH. pH is even decreasing in the deep hole. It's starting at 2.8. You see here the green scale, and then it's decreasing even. So there's hot, saline, and acid water coming into that hole, and from that hole then, of course, into the lake, which also explains why this lake water is so acidic. So let's combine these two data, the bathymetry, the fault mapping, and the geochemistry. Before we did this study, we were aware of the faults we saw in outcrops, and we knew a little bit about the permeability from the discharge measurements. Then after the fault mapping with the bathymetry, we were able to draw more faults here in gray and black in the middle. So the black ones are the previously known, and the gray ones, the newly discovered ones. And then if we add on top the geochemistry, we can even talk about the permeability. At least we know if they're rather permeable or rather impermeable. We cannot give numbers, but we rather know if there's fluid flow happening close to these faults, we know there must be some permeability. That's why we label them in red. And we see this along the western part mainly of the lake, but also we used the well data, which is also in red here now, the quite productive wells. And there are some non-productive wells close to non-permeable zones and faults. So we call this a new exploration method, or a combination, nice new combination of bathymetry for fault mapping and geochemistry for mapping fluid flow pathways and understanding where the fluid is coming from at depth. This was an example from Indonesia. Last year we have been on fieldwork in Turkey and did the same approach. We used that again for a volcanic lake. You see here a smaller one with a diameter of 600 meters, volcanic lake in central Anatolia. And you see again that we see in the bathymetry study on the left lower corner, these deep holes. They are not that deep, but they are, again, 25 meters and really steep and really thin, like a cone. This is, of course, this time it was more expected, but it surprises me again and again to see this, what is Mother Earth telling us here. And then in the more brown-colored pictures, you see how the boat is driving. On number A, you see the lake bottom side scan, so the view from the boat to the lake bottom. And the DH1 is one of the deep holes here. You see again this circle structure. And then close to that on C, you see also gas bubbles rising here from the deep hole. And on the very right, it's even more clear. You see a kind of pockmark, a circle structure on the very lower picture, a circle structure, and then on the top more the gas bubbles which are rising, and soft ground, and really a hole in the lake bottom, which we could have observed with our side scan and down scan images. So again, we see that fault structures which we observe onshore in outcrops and which are mapped already in previous studies, we see that they continue into the lake, and that these fault structures meet exactly at these deep holes. And then because they meet and because they are active, these faults kind of, they cause fluid flow from these holes. So they are permeable areas again, and we were able to measure them here again and kind of prove our concept, our new approach. So I promised also to speak a bit about the operational side of geothermal systems and how to operate sustainably. So let's jump to the monitoring aspect of geothermal systems. You see again the same map from the same geothermal field, now showing you the hot springs in this area. And in the beginning, when we started mapping this field, and this is back in 2010, I visited the field for the first time. We now have a nice database about 8 years, I think now. We did measurements and took samples in the hot springs, and we saw that the hot springs are basically mainly located along faults, which is not that surprising because we need some permeability, and we saw before that the faults provide some permeability. What is interesting that we see two different water types here. So we have acidic springs more in the center of the field, closer to the lake. And then we also have more neutral springs off the center. Then what happened when we came back in 2018 is that we mapped the same hot springs, but we saw a lot of difference. You see now, close to the lake, there were acidic springs, but now all of them are acidic. Only the springs in the very northeast, which are probably even out of our geothermal system, are still neutral. But all our hot springs changed their fluid composition. And not only the fluid composition changed, but also the physical parameters of the springs. So you see that before, this one spring I show here in the pictures has been 15 meters in diameter, but now it's 9 meters. You could argue this is due to rain and so on, but it was measured in the same month, not at the same day, but in the same season. So we see a clear physical change. There's even a change in color of the water. So it's more milky. There's more scaling and precipitation happening here. So something is changing in the system. And we can observe this in the hydrochemical parameters. A master student working with me now as a PhD, Lily, did a more detailed study on that and measured the pH and plotted that. And you see what we observed before. All the hot springs lost values of pH, so all of that is decreasing. The salinity, electric conductivity now here is increasing. And then we used this nice Gegenbach plot, which is very common in geothermal research, to plot all our well data, which we had, the hydrochemical composition of the wells in this diagram. And we see that there's a clear trend. It's a bit messy with all the colors, but there's a clear trend of all the wells towards more chloridic water. So there's more acidity. There's an increase in chloride and salinity. And what I don't show here, but I can tell you, is there's also an increase in dryness and a declining brine composition here. So that all shows us that there's boiling happening in this system. And this is so important to see this and to observe this, because boiling in a geothermal system is not a good factor for long-term sustainable use. That means the brine, the water level is decreasing. You have more void for steam and boiling, which is in the first moment good, because you can produce more steam, but at the end you lose pressure. We did a similar study in a field in Tanzania, where we more focused on the source of fluids, because now the question would be, if we lose pressure, if we lose fluid, where is the water coming from? And in this field, they are not producing yet, but there's a lot of data from the hot springs already since years. And we plotted them, and we already see that there's something happening even without exploitation, without operating fields. So it's even important to measure that before you start operation, to also have a good baseline. And using this, it might look a bit complicated here, this model we used, but we were able to understand the fluid composition, from the fluid composition back to the fluid source. You see 3 different geological layers in pink and red and in gray, and you see different hot springs on the top with different names. And the arrows show you where the fluid is coming from, and we were able to trace that back only using hydrochemical parameters. There's no drilling, there's no well, but we already understood how the fluid flow going on in this subsurface, in this field where they plan to drill soon, and where it's important to understand where the water is coming from. Now, let me also show you, give you an insight into an operating field of a middle enthalpy field. Here, an example from Lithuania. And what you often observe, now we come back from the field, from the hot springs to the wells. I plotted the injectivity index, which is the fluid flow you inject per pressure you need to inject this fluid amount. And these 2 curves show you 2 different wells, 2 injection wells. And you see that the injectivity was quite high in the beginning, and then is decreasing. That is very typical, and this often happens within the first 5 to 10 years. First it looks nice, first it looks very simple, but I will show you now a kind of negative example how things can go wrong if you don't monitor your system, and how you then run into problems operating safely and efficiently in a long term. The pictures show you 2 examples from scaling on site. So a pipeline which is scaled with the silica scaling, and at the bottom from this Lithuanian plant, gypsum crystals growing inside of the whole system. So again, the same graphs, the same trends. 2 wells losing their injectivity, and on top now plotted also the measures they took, stimulation measures. They cleaned the system, they acidified their wells and their whole system. They even drilled a sidetrack, and they also used radial jet drilling, which is here at the very right, 2015 AJD, where they drilled smaller holes within the casing to overcome probably formation damage which is close to the well, and to connect the well to the higher permeability far from the well. So they did a lot to recover the injectivity, and you see that sometimes it was possible to increase the injectivity, but then it dropped again. And that happened over several years. You see here it's more than 15 years they tried to recover the initial injectivity, but that system is unfortunately it's lost, and we couldn't recover that. So even more important is to understand why this happens and what we can do about that to avoid this. So let me show you some reasons for injectivity decline from this example, and it's representative for a lot of geothermal plants actually. So there's of course precipitation. This is commonly known. This is quite well understood, but still not well studied before geothermal systems go into operation. You see here a sample I took and just took into this glass bottle and put it into the lab. And after 1 year, I looked again and I saw these mini gypsum crystals growing here. This is nice to see, geochemistry live, but it's not nice to have that in the pipes. In the lower picture, you see that, and I tell you that they had to stop the whole operation and clean all their pipelines and all their valves. They had gypsum crystals big as my arm. And this is not something you want in your system. Then we also checked for fines migration, and we found that the filter system actually doesn't work. You see this in the statistics. We took the measurements of fines in the water actually, and on the top before the filter, and the filter is 1 micron in size. So if before the filter there are particles with 4 micron, this can happen, this is quite normal. But after the filter, and at the lower picture, this shouldn't happen anymore. So the filter should actually take out all these 4 micron up to 60 micron particles in size. So there's something wrong with this filter system, and this is the water and the particles you finally inject into your porous medium. And you don't want to have that in your pores if you want to inject the water in the long term. Then we took also even finer filters to observe bioactivity, and we saw that we had this brown slimy film, which was biofilm, and on the lower picture you see a sample from the filters actually. And there's a corrosion material. You see on the right side, this is basically sand. This can also happen. This is quite normal that sand is produced if it's a loose sedimentary aquifer, but there are also quite big corrosion plates and particles, which is something to worry about a bit. So you see here a zoom in and the filter residual, which is magnetic. So none of these reasons for injectivity decline you want to have. And we now also put that back into the history of this single geothermal power plant. And first, what happened first in this case is the precipitation in the pipes, the gypsum precipitation. So they stopped the plant, they cleaned everything, and they acidified also the wells to get rid of all the rests of the precipitation. After that, they realized that there's fines migration. There are a lot of fines in the filters, and we assume that this also happened because they used HF even, and that can lose your clay and resolves a lot of smaller particles. So they decided not to acidify too much anymore, but rather use inhibitor to stop the precipitation of gypsum, which worked out quite nicely, so they don't have any precipitation problem anymore. But the inhibitor is phosphorus-based, And this phosphor is nice food for microbiology. So they are happy that they are living in a nice 40 degrees warm water at 2 kilometers depth, and even fed by the people using the inhibitor. So we see an increase in bioactivity, and the final outcome of that is this organic filter residual, which you can think is that's also blocking the pores in the underground. And this bioactivity in the underground is also known that it causes corrosion because it kind of eats away your casing of the wells. So you have a circle here, everything interacting with each other, which you don't want to enter when you're operating a geothermal system. You rather, some of these things you can understand before. You can take samples from the plants, you can check inhibitors, you can check bioactivity, you can check your filters if they are working. So it's so important, again, I say again and again to every geothermal operator, to monitor your system so you don't enter this bad circle of injectivity decline at the end. So better avoid, I say, and for that I come to the end of my presentation and want to shortly introduce our new project Hadi already mentioned, called EasyGo. It's an ITN interpretive training network, which is led by me as a project coordinator. It's called EasyGo Efficiency and Safety in Geothermal Operations, and we will focus on things I mentioned today with 13 PhD students located at the Idea League universities, which is TU Delft, Aachen, ETH in Zurich, and Polymere in Milano. We will have a doctoral school with European joint degrees. We are working on large-scale infrastructure and very happy that we can work on-site in the underground labs in Switzerland, on real power plants in Italy and Germany, and also at the dub well, which will be drilled in Delft. We were very happy and lucky that we could attract 10 industry partners from all these countries, which are really enthusiastic and happy to also educate our students and to be partner in the project, give access to their knowledge, to their factories, to their labs, and help us educating the next generation of geothermal experts. The basic research questions of these 13 PhD students is: how do we run geothermal systems efficiently, and how do we run them safely? We will have advanced monitoring systems for that. We will have real-time simulations, quite advanced. Some of the PhD students will work on development of system components, and some of them will also design components, work on turbines, for example, related to operational parameters. The staircase you see here is our personal development staircase. We not only want to teach the students on the science and research, but also want to teach them how to survive in the academic or industry life then after they can graduate. So with that, thank you very much, and I'm happy to answer your questions.
Thank you very much, Maren, for this very interesting talk. I see already some questions texted already in the platform. Without any further ado, Sebastian, please, the stage is yours.
Thank you indeed, Maren, for this great talk, and it highlights very nicely how important proper geological and geochemical understanding is for both the exploration side and the production side. As Hadi said, we have lots of questions already coming in, and I hope there will be some additional questions. So start a little bit with the order they came in. So the first one is from Ralph. He wonders why water can disappear in the rock, where it's usually the pressure inside the formation should be higher due to higher temperature.
So, yes, of course. Well, that is, as you said already, really depending on the system. If it's a sedimentary system, it depends on the water flow in the underground. So geothermal systems should be set up that the injection is probably out of the system if you're afraid of a cold water breakthrough, or even before the production well in terms of flow direction to keep up the pressure. Of course, you always need some pressure, and that's why I showed this injectivity index to put the water down. Only if there's a non-pressurized aquifer, so to say, you can just pour down the water, but this is really rare. You always need a pump to inject the water.
So staying on the hydrological side, Bill Rossman, one of the former speakers, asked if the temperature is high in the deep holes and lake bottoms, why doesn't lower density of hot water make it rise, mix with the rest of the lake water? Is the hole too narrow, or does the higher salinity make the hot water more dense? Why is that? Why do you not see?
Yeah, that's true. Probably our measurement, our network was not too dense to see the really conductive cells in the lake. But I think that the water inflow into the hole is too strong than to allow a convective cell within the hole. It's so narrow at the bottom of the hole. It's only, I think it's 2 or 4 meters we measured. And at the beginning, it's like 10 meters. So it's really narrow. And if there's even inflow, there's not much mixing in a vertical sense, I would expect.
A follow-up question, and changing topics a little bit now from Bill is, he wonders if you can distinguish between flow and fractures and faults and the permeability of the rock. So does the tracer data give you any indication what is flowing on permeability?
If the question is related to the tracer test we did in the rivers, we clearly see that the loss is across the fault. So our measurements was clearly shortly before the fault and shortly after the fault. So it was really related to the permeability of the faults. Of course, we can also lose water into the rocks. But in this case, for example, we were working in a volcanic area, and volcanic rocks are known for low permeability. We measured also rocks cores from the wells, and we have a permeability of the power to minus 14 or 15 even. So I don't expect a high permeability in the rock itself, a basic permeability. So it's really related to fractures and faults in this environment.
Thank you. Soren, Popeye Soren comments, interesting. Can one measure or estimate the changes in the rock properties that you to increased acidity?
If I understand that correctly, you mean a change in the rock property? Yeah, because maybe some dissolution happens. So I assume it's going that direction. Well, yeah. we didn't because we have cores from wells, but we don't have newer cores. So they only cored in the beginning with the exploration wells. But I would assume for sure that there's something happening due to increasing acidity. There's for sure dissolution happening if the acidity is so high or low, whatever you want to say. The pH is so low, like 1 or 2, like we measured. There's even silica dissolution happening. So there should be dissolution, and that is also probably why I showed this one example with the hot springs, that there's a milky water nowadays in the hot springs because there's much more dissolution happening and much more particles in the water. For sure there's something happening like that, but I don't have a real measurement on this.
Okay. Is there just sort of curiosity question from my side? Is there anything, so you mentioned the colors changing, is there anything else that could hint about ongoing dissolution happening, or anything in the production data, pressure fluctuations at the wells that could indicate that you're actually creating new permeability or destroying permeability? Or is that all masked by the really complex geochemical systems, the geochemistry that constantly involves precipitation?
Yeah, well, as you said, it's a really complex system. So on the one hand, for sure, you have dissolution because of acidity, but at one point there should also be precipitation in some wells. But we see that the system is changing. I couldn't show all the data for today, but we see that some wells are kind of reactivated and now could be used as production wells, which have been non-productive before. So that could be an indication that their permeability is increasing in some areas. Then new fluid pathways are opening. Also, they drill new wells and suck out from the reservoir in different parts. I said there's boiling going on. So there's for sure a change in permeability, and this is something Lily, my PhD student, started just this year, will look into to understand back from the geochemistry. I just gave an insight from today to look a bit more into detail and understand better how these fluid pathways changed. But for sure, they are changing us.
Thank you. So another question from Ralph, and he wonders, do these crystals, you mentioned crystals the size of your arm, form after a temperature decrease or already within the production well due to pressure drop?
They formed basically due to pressure drop. There was no temperature decrease observed in this power plant. It's about 39 to 40 degrees, still stable, this reservoir, even used since a long time, but there's for sure pressure drop, and that's the basic reason why these crystals formed.
One question from Wilhelmine, and I wanted to ask you the question as well, but so Wilhelmine, thank you for the nice presentation. Is your research on volcanic reservoir also applicable on non-volcanic reservoirs, for example, in the Netherlands? So how portable is your geochemical, hydrological exploration to other systems?
Yeah, for sure. We are not that lucky to have hot springs in the Netherlands, which would be nice to observe them. But for sure, the techniques, the monitoring techniques we developed in this volcanic environment are for sure applicable in all geothermal systems. Of course, you always have to remember that in the Netherlands, we are dealing with sedimentary aquifers, and in volcanic environments, more with fractured and folded environments. But for example, this bathymetry study we now tried in volcanic lakes. I have plans to use them also in Central Europe, and already have a lake in mind which is non-volcanic, but reported to me to be the hottest lake of that country we will study. And I'm very curious to test this method, but I'm sure we can observe. And I also see other studies before where pockmarks and these kind of deep holes where fluid is coming out is happening in non-volcanic environments. So these techniques we developed there are applicable, and maybe let me explain why we developed it there, because I mentioned I'm studying this field since 2010. We have a good database of 8 years now, so we could benchmark our new methods, our new approach. We could be sure that it's working, and we had other data to confirm and to check back and forth before we go into a newer field like Netherlands or Central Europe, where we would now be in the next step and try this method, because we are sure it's working now.
Excellent, thank you. We do have a question from Willem. Just put this up. So there's quite a few questions coming through at the moment, a couple of questions coming through on the EasyGo project. But before we go to this, Willem wonders, the pore pressure of the milky hot water that you described, is that the same as the pore pressure in the colder waters? And if there are differences, is there any impact on the effective stress on these hotter rocks?
Yeah, I cannot give you numbers about the pore pressure. We don't have measurements on that. The stress field is basically driven by the tectonic activity in this area. There's a subduction. Actually, it's an island with a subduction from the north and from the south, just meeting beneath this volcanic and geothermal system. So it's quite complicated, and I think that's the main driver for the stress change. I think local stress changes can happen due to dissolution and precipitation, but we don't have real measurements from the wells on that. But it would be maybe a nice laboratory study to take the samples. I still have to test them on stress measurements using dissolution precipitation processes.
Okay, so let's switch for a moment to the questions regarding the EasyGo project. So in your last slide, Mark wanted to ask the question, thank you for the presentation. Could you please comment more on the real-time simulation process that you have mentioned? What's the major objective and method?
Mm-hmm. I can explain shortly. Otherwise, you can also check the homepage where all the small research projects are described in detail. The simulations basically, as all the whole project will focus on real-time and on-site measurements in real scale also. So we basically use measurements at the large infrastructure and to simulate them at the same moment if possible. This is our aim. And at the same scale also. So not to scale up from laboratory experiments to the real scale, but really use these large infrastructure to use kind of online monitoring systems. We
have a question from Ven. We'll probably ask a question. There's a lot of possible future PhD students who are interested in geothermal energy asking themselves, who watching live or will be viewing your talk later on, my question is, when will you begin inviting applicants for PhD positions under the EasyGo interview? So more briefly, if you want to become part of that exciting project, what do you need to do?
Yeah, thank you for that interest. As Hadi mentioned, the application deadline just passed 10 days ago, and now we are reviewing the 1,500 applications, and we choose the most excellent ones, the best ones. And if you're among them, you will be invited for an interview probably within the next 2 or 3 weeks.
Okay, thank you. 1,500 applications, that's fantastic. That's great interest.
That's great.
I do have one more technical question from Kasif. He wonders, is it possible to operate CPG system in comparatively younger and colder basins? What would be the optimal conditions? He's very interested in that.
I think the CPG system refers to the CO2 to power, or CO2 geothermal systems. I think there's quite an overlap between the CPG systems and geothermal environments. It's just the fluid which is changing, and there are some thermodynamics being even more feasible using CO2 as a driving fluid. We have research projects on that, at least proposals we are writing, and have ideas how to test that. And some of the research projects, some of the PhDs will study that even in our EasyGo system. Yeah, maybe because of the thermodynamic fluids, but then I would refer to my colleagues at ETH, Martin Saar, who's the expert on that. It could be more feasible, or it could be nicer to use it in colder basins compared to classical geothermal systems. But we are really at the beginning of studying that to make a sound interpretation of that.
Thank you. And then Diana, who welcomed us from Denver at the beginning of the talk, wonders, do you have any similar projects that are planned for Latin America or Caribbean geothermal basins systems?
I don't know of any projects planned or going on. I know about a project which has taken place in Mexico, a European-Mexican collaboration which just ended. It's called the GMAX project, Horizon 2020 project. I was involved still when I was in Potsdam. You can check the homepage on the results on that. There are a lot of publications now coming out. I know that there are attempts to build up new projects on at least fractured fluid flow, which is run in Chile, as far as I know. But I don't have information if that is already funded.
Okay. So time is slowly coming to an end, but I take one more question from Andrew Seat, who also welcomed us from Calgary this afternoon, our time. And Andrew wonders, did you attempt to histimate well injectivity during the scaling and stimulation cycles? It would be useful for predicting performance, implementing proper treatment programs. Apologies.
Yeah, that's actually a nice idea. We didn't do that yet. I'm not a modeling expert also, but I have good colleagues to work with. I probably can do that in the future. I think it would increase our understanding a lot to history match that and look into more detail rather than only point data. But thanks.
And Andrew, who I know well, I can see him thinking that one of our colleagues here at Heriot-Watt University, Eric Mackay, who's worked on mineral scaling for many years, for 20 years, they probably would be really interested in teaming up with you. And I'm thinking about how we can manage the scaling issue in these geothermal wells. Our time is up, so thank you everyone for all your questions. Thank you, Maren, for taking the time to give an excellent presentation, answering all the questions so diligently. And I hand over to Hadi for some last comments now, announcing our next speaker.
Yes, indeed. Thank you, everyone. So the next speaker is Paul Zeppenfeld, Vice President of Shell Company. Paul is going to speak about the subsurface in the energy transition. So stay tuned, happy, healthy until next week, the same time, 4 p.m. Central European, 3 p.m. British time, 7 a.m. California. Andrew, I don't know what time would it be in Calgary. Please tune in and let us all collect together again and have this great talk that is coming up next week by Paul, and see how also Shell is contributing to this energy transition move as well. So until next time, all the best and goodbye.
Thank you very much, everyone. Bye-bye. Bye. And thank you, Maren.